Hey there, fellow adventurers, and welcome. I'm NerdTeach, and I am so glad you've joined me on this quest. Today, we're going to dive deep, deep into the magical world that lives inside our computers, all to uncover a secret language that makes everything, well, work. It's going to be a fun one. Okay, let's kick things off with a little challenge. Imagine you're a powerful code mage, right? But your most trusted spells, division and modulo, they've been locked away. So how would you figure out if a number is odd? Kind of sounds tough, doesn't it? Well, guess what? Your computer solves this exact puzzle in a flash all the time. The answer isn't some super complicated incantation. No, it's hidden in the computer's native tongue, a language that's built on something way more fundamental than the numbers we use every day. So come on, let's peek behind the curtain and explore this secret world together. So to really master the computer's magic, we first need to learn its alphabet. And you know what? It's surprisingly simple, but it is the foundation of absolutely everything we do in coding. You and I are used to our 10 digits, 0 through 9, but the computer's world, it's much, much simpler. It's built on just two magical runes, a 0 and a 1. And believe it or not, every number, every letter, every single color on your screen is really just a long string of these two symbols. All right, now that we've got the alphabet down, let's see how these runes can represent all the numbers we use. I mean, it's pretty easy with positive numbers, but the real magic, that happens when we start dealing with negative numbers. This is such a great question, and it's a puzzle that early computer scientists really had to crack. I mean, you can't just stick a minus sign in front of a bunch of ones and zeros, right? The computer needs a special spell to understand that a number is negative. Any guesses on how it works? Well, the solution is this really clever system called 2's complement. You can think of it like a spell book just for negative numbers. And in this system, the very first rune, so the leftmost bit, it has a really special job. It's the sign bit. If it's a 0, the number's positive. And if it's a 1, well, you guessed it, the number is negative. So how do we actually cast this spell for, say, -5? It's a 3-step ritual. First, we write +5 in binary. Easy enough. Then we cast an inversion spell, flipping every 0 to a 1 and every 1 to a 0. And for the final step, we just add 1. And poof, just like that, 1111, 1011 is how the computer sees -5. Now here's a really curious side effect of this spell. Because of 2's complement, the range of numbers you can store is a little lopsided. You can actually store one more negative number than you can positive numbers. This is a classic interview question, and it can totally trip you up in problems like reverse an integer. It's a small detail with really big implications. Okay, so now that we can read the runes, it's time to learn how to change them. These are the bitwise operators, or as I like to call them, our magic spells. They let us talk directly to the CPU and manipulate the ones and zeros ourselves. And this is how we write super fast, super efficient code. Welcome to our grimoire of bitwise spells. First up, the AND operator is our masking spell. It's perfect for checking if a specific rune is active. The OR operator is our setting spell, which guarantees a rune is turned on. Then there's XOR, our toggling spell, for flipping a rune from on to off or off to on. And of course, the NOT spell, which we've seen before. That one just inverts everything. But we're not just changing runes, we can also move them. These are the shift operators. A left shift is kind of like a teleportation spell that moves all the runes one spot to the left, which is basically the same as multiplying by 2. A right shift moves them to the right, which divides by 2. And let me tell you, this is so much faster than regular math. But a word of caution here, adventurers, the right shift spell works a little differently in the worlds of Java and C++. You see, Java has two versions, one that keeps the sign of a negative number, and another one, the triple arrow VVV, that always fills the empty space with a 0. C++, on the other hand, only has the sign-preserving version. To get that other effect, you need a special incantation, casting to an unsigned int. This is another classic interview question, so definitely pay close attention. Now this is where it gets really, really interesting. We can start to combine these simple spells to create powerful, ancient techniques. These are incredibly elegant solutions to problems that might otherwise seem impossible or just really, really slow. Okay, here's our next challenge for you code mages out there. We need a function that can instantly tell if a number is a power of 2. Now sure, you could use a loop and just keep dividing by 2, but that's the slow way. A true code mage uses a single, elegant, bitwise spell. And here it is, the ancient incantation. Now, it might look a little mysterious at first, but this one single line of code is all you need. It's clean, it's instant, and it's just pure bitwise magic. So let's unravel the secret of how this powerful spell actually works. And this just brilliantly illustrates the trick. Think about it. A power of 2 in binary is always a single 1 followed by a trail of zeros. When you subtract 1 from it, you get a number that's all ones. So when you use the AND spell on them, there's absolutely no overlap. The result is always 0. For any other number with multiple ones, the result will always be more than 0. It's so simple and beautiful. Now, let me tell you about another famous spell, this one from the great wizard Brian Kernighan. What if you need to count the number of glowing runes, or set bits, the ones in a number? Well, instead of checking every single bit, this clever algorithm just jumps from one glowing rune to the next. The magic is actually in the same trick we just learned, n and n-1. It's amazing. Every time you cast the spell, it finds the rightmost one and magically just turns it off. So all you have to do is cast the spell in a loop and count how many times it takes for the number to become 0. The number of spells you cast is the number of glowing runes. So you might be thinking, okay, NerdTeach, this is cool, but is it actually useful? And the answer is absolutely. These spells and incantations are like a treasure chest of tools that will make you a better programmer and totally help you shine in those technical interviews. So why does all this matter? Well, because you can write code that runs incredibly fast. You can solve what seem like really hard problems with these single clever lines of code. You gain a much deeper understanding of how your computer actually works, and you can perform some amazing tricks like using the XOR spell to find the one number that doesn't have a pair in a giant list. And just look at how beautifully this translates into real code. Whether you're working in C++ or Java, the incantation is exactly the same. So you see, this isn't just theory. It's a practical, powerful tool you can add to your spellbook right now. Now, if any of this felt confusing, I want you to know that it's completely okay. In fact, it's a really good sign. Every single great programmer that you admire once felt lost exploring these ideas. Confusion is just a signpost that tells you that you're on the path to true understanding. Wow, we've uncovered the CPU's secret language and learned some of its most powerful spells. But our adventure is far from over. In our next quest, we're going to journey into the winding forest of loops, where you can find powerful solutions or get lost wandering in circles forever. I really can't wait to see you on the next adventure.
Hello, adventurers, and welcome back to our magical world of code. I'm NerdTeach, and today we're setting off on a brand new journey. We're going to dive deep into the world of number magic, a place where even the most simple-looking spells can hide some really surprising twists.
So, have you ever felt this? You write some code, you look it over, it seems absolutely perfect, and then you run it and it just shatters. For no reason you can see. Trust me, it's a feeling every single person who has ever coded has felt. It's not a sign you're failing. It's a sign you're right on the edge of discovering something really, really important.
And today, that's exactly what we're going to do. We're going to become trap finders. We're going to uncover two of the most common sneaky traps you'll find when you're working with numbers. And by the end of this, you'll have two new superpowers to protect your code for good. Okay, you ready? Let's get into it.
Our adventure starts with a gem mage who's trying to organize their collection. All they need to do is take the ID number from a magic gem and just reverse it. Sounds easy enough, right? But what kind of hidden dangers could possibly be lurking in a spell this simple?
This, my friends, is the quest of the Shattering Crystal. It's a classic puzzle, almost a rite of passage for every programmer, and it teaches a really powerful lesson about the hidden limits of our own magic. So the spell itself is pretty straightforward. You just peel off the last digit from the number, you add it to the beginning of a new number you're building, and you just keep doing that until you're done. In our code spellbook, peeling off the digit uses the modulo rune, n%10, and adding it to the front uses this little bit of magic. Reverse equals reverse times 10 plus digit. It's a really beautiful and simple piece of logic.
Okay, so our gem mage picks up this one super sparkly gem, and it has this ID number on it. They get ready to cast their simple little spell. Seems fine, right? But this particular gem holds a secret. You see, in the world of programming, numbers aren't just infinite things floating in space. They have to be stored somewhere. And our number is being stored in what's called a 32-bit signed integer. Now, that's just a fancy name for a magical crystal chest that has a fixed, unchangeable size. It can only hold so much.
The absolute biggest number that this crystal chest can possibly hold is just over 2.1 billion. Now that sounds huge, doesn't it? But you would be amazed how quickly we can run into these limits in programming. Our original number fits inside just fine, but what do you think is going to happen when we reverse it?
The mage casts the spell. The new number starts to take shape, 9, then 96, then 964. It just keeps growing and growing until the final number, over 9.6 billion, is way too big. It can't be contained. The magic backfires, the chest overflows, and it shatters. This is called an integer overflow, and it's the first hidden trap we've uncovered. Now, it is so easy to get frustrated when this happens, but I want you to listen to this ancient secret. This happens to everyone. Seriously. Falling into this trap means you're actually learning. The goal isn't to write some super clever short breath spell. It's to write a careful, thoughtful one that sees these limits come. So how do we fix our spell? Well, the solution is a really simple but powerful shift in how we think. The trap is to do the multiplication first, and then just hope for the best. The real spell, the powerful one, is to check if it will fit before we even try.
The protective word we need is just a simple question we ask our code before it does anything. We're basically saying, hey, before you go and multiply my new number by 10, are we already getting a little too close to the chest's limit? By checking ahead of time, we can stop the disaster before it even starts. Okay, let's look at what this protective word looks like as an actual spell in our spellbook. This is a perfect example of defensive magic. This first line is kind of like peeking into the chest and asking, are we already past the last possible shelf? The second and third lines, they handle a very specific edge case. What if we're right on the very last shelf and the next digit we're about to add is bigger than a 7? You see, since the biggest possible number ends in a 7, anything bigger than that would definitely cause an overflow. This is what being a careful programmer really looks like. And hey, don't worry if you're using a different spellbook. In C++, the logic is exactly 100% the same. You just use int max, which you can find in the ancient CI limit scroll. The core idea, that check, then multiply principle, it's a universal truth in the world of coding.
Awesome. Our first quest taught us how to be careful about limits. Our next quest is going to teach us how to be clever about time. We journey now to an alchemist's workshop, where the problem isn't the size of the chest, but the relentless ticking of the clock.
So, our alchemist needs a big supply of a very special ingredient, prime gems. These are numbers that are, well, pure. You can't divide them by any other number except for 1 and themselves. Like 2, 3, 5, 7, 11. They're like the fundamental building blocks for all other numbers.
And the alchemist doesn't just need 1 or 2. The recipe calls for a list of every single prime gem, all the way up to 10 million. I mean, how would you even start a task that big?
Well, the most obvious way is to just check every single number. For each number up to 10 million, you could test if it's divisible by any smaller number. But on a regular computer, this would take a long time. Minutes, maybe even an hour. Our poor timekeeper clock character is getting tired just thinking about it. This brute force method, well, that's our second hidden trap.
But of course, there's a smarter way. Welcome to the quest of the Prime Garden. This is where we learn that sometimes the most powerful magic isn't about working harder. It's about working smarter. We're going to learn an ancient and really beautiful enchantment called the Sieve of Eratosthenes.
Imagine a giant garden where every number from 2 up to 10 million is a potential gem, just waiting. The sieve starts with the very first prime number we know, 2. Then a magical ripple goes through the whole garden and it marks every multiple of 2, 4, 6, 8, all of those, as not prime. We basically turn them into dull stone because we know for a fact they can't be prime if 2 goes into them.
Then what? Well, the enchantment just finds the next glowing gem in our garden that hasn't been touched yet. That would be the number 3. So it must be prime. The spell fires off again, marking all the multiples of 3, like 6, 9, 15, as stone. We just keep doing this over and over, and all the gems left glowing at the end, those are all the prime.
And this shows the difference so perfectly. If that slow one-by-one method takes, say, 100 ticks from our timekeeper clock, the sieve enchantment takes just a tiny fraction of that, maybe 5 ticks. For our 10 million number problem, this is the difference between waiting around for minutes and getting your answer in the blink of an eye. That is strategic magic.
And with that, our 2 quests are complete. You face down the shattering crystal of overflow, and you've navigated the alchemist's endless task. You have absolutely earned 2 brand new superpowers today.
First up is defensive magic, the wisdom to always check for boundaries before you act. And second is strategic magic, the ability to pick a smart, efficient algorithm over a slow, brute force one. And all of that brings us to the most important magic we learned today. Thinking like a programmer is all about balancing being careful with being clever. So please, remember that feeling of confusion? It just means your brain is leveling up. In our next quest together, we're going to journey into the forest of repetition, where we'll learn all about loops, powerful spells that can either be your greatest ally or your most dangerous trap. Until then, happy coding adventures.
You know, most people think coding is about being some kind of genius, but it's not. Not really. The real secret, the magic, is learning to see the hidden patterns all around us. Today, our quest is to uncover some of the most powerful patterns in all of programming. So, are you ready? Let's begin. All right, so every good quest starts with a puzzle. I want you to imagine you're the keeper of 2 magical lighthouses. One of them blinks every, say, 18 seconds, and the other blinks every 24 seconds. Now, there's a legendary ship out there, and it can only find its way to port if they shine together. The big question is, how can we predict that exact moment? So, a tale of 2 rhythms. Okay, let's dive into this. And I want you to know, this isn't just some abstract math problem. No way. This is a quest to find the secret connection, that deep harmony between these 2 cycles. If we can solve this, we'll have the power to guide that ship home, safe and sound. Now, listen, if you're feeling a little bit lost or confused right now, I want you to know that's perfectly okay. In fact, it's a really good sign. That feeling, that's how you know you're on the verge of learning something new and powerful. We're going to walk this path together step by step. The Great Harmony Crystal. Okay, so every quest needs a magical tool, right? And for our quest, we have the Great Harmony Crystal. This special artifact, this is what holds the key. It's going to help us understand that deep core connection between any 2 numbers, or in our case, the rhythms of our 2 lighthouses. So what is this crystal really? Well, I want you to think of our lighthouse cycles, the 18 and the 24, as 2 big ancient gears. The harmony crystal is the largest possible piece, like a gear tooth, that fits perfectly into both of those gears. And in the world of math, we have a name for this, the greatest common divisor, or GCD for short. It's just the biggest number that divides both our cycles without leaving any remainder. Okay, so how do we find this crystal? We use an ancient ritual, a clever little dance of numbers from a mathematician named Euclid. Here's how it works. You take the larger gear, your bigger number, and you see what's left over after you divide it by the smaller one. You know, the remainder. Then that remainder becomes your new small number. You just swap them. And you keep doing that. You swap and shrink, over and over, until one of the numbers just becomes 0 and vanishes. And the number that's left standing, that, my friend, is our harmony crystal. That's the GCD. Of course, this ancient ritual has a written spell, which is what we call code. Let's look at C++. We use a while loop, which basically says, keep doing this until b becomes 0. This line here, a%b, that's how we find the remainder. And std swap ab, well, that's us swapping the gears. Now, look at the Java version. The logic is exactly the same. We just use a little helper, a temp variable, to do the swap. See, both of these spells perform the exact same magic. They just use slightly different words. The cycle of alignment. Yes, we did it. We have found the harmony crystal. We now know the GCD of our 2 lighthouse cycles. And with this powerful artifact in our hands, we can finally solve the original puzzle and figure out when those lighthouses are going to shine together. So, this moment of perfect synchronization, that's what we call the cycle of alignment. In the world of math, it's known as the least common multiple, or LCM for short. And here's where the magic really happens. There's this beautiful, simple relationship. To find the LCM, you just multiply your 2 numbers together and then divide by the GCD we just found. It's that simple. But wait, a word of caution, brave adventurer. If you just rush in and multiply A and B together first, you might accidentally summon the dreaded overflow beast. This nasty creature appears when the result of your calculation gets so huge that the computer literally can't store it. Your spell breaks, your program crashes, it's a mess. So how do we defeat the beast? It's actually a really clever trick. The crucial part is the order in which we write our spell. We take the safe path. Instead of A times B divided by GCD, we do A divided by GCD times B. See what we did there? We divide one of our numbers by the GCD first. This shrinks the number down to a manageable size before we multiply. It gives you the exact same answer, but it keeps your spell from breaking. No beastie. Journey to the clockwork realm. Wow, our quest has already taken us pretty far, but now an even more magical land awaits. It's time to journey to the clockwork realm. This is a strange and wonderful place where numbers don't stretch out to infinity. Instead, they loop back on themselves, kind of like the hands of a clock. Just think about a regular everyday clock. The hour hand moves forward, it gets to 11 o'clock, then 12 o'clock. So what happens next? It doesn't go to 13, does it? Nope, it wraps right back around to 1. And believe it or not, this simple little idea from a clock face is one of the most powerful concepts in all of computer science. Welcome to the world of modular arithmetic. That's the official name for the magic of the clockwork realm. Here, we only care about the remainder after division, and that number that everything wraps around, like 12 on our clock, that's called the modulus. This magic is absolutely essential for things like cryptography and game development, where we need to keep gigantic numbers under control. So in this realm, we have a few special rules or runes for doing math. We can add, subtract, and multiply just like normal, but after every operation, we always take the remainder using our modulus. That's what keeps the numbers inside the realm. Now there's a special little trick for subtraction. To make sure our answer never accidentally becomes negative, we add m, the modulus, before we take the remainder. It's a neat trick to keep everything positive and within the cycle. The reverse incantation. Okay, so we've got runes for moving forwards, right? Adding and multiplying, but what about moving backwards? What about division? This, my friends, is the next great puzzle we have to solve here in the clockwork realm. I mean, think about it for a second. In a world that only works with remainders and loops, how do you even divide by a number? It's not straightforward at all. We can't just use the normal division symbol. We're going to need a new kind of magic, some kind of special key to unlock this whole operation. And that key is called the modular inverse. The easiest way to think about it is like a number's special opposite in this world. It's a number that when you multiply it by the original number, the answer comes out to exactly 1. And what that means is, instead of trying to divide by a number, we can just multiply by its inverse instead. It's how we undo multiplication here. Okay, but how in the world do we find this special key? Well, luckily for us, ancient mathematicians uncovered a really powerful secret. It's called Fermat's little theorem. It says that if our modulus, m, is a prime number, then any other number, b, when you raise it to the power of m minus 1, will always equal 1 in this clockwork realm. And that right there, that is the key to our solution. If b to the power of m minus 1 is 1, then with a little bit of magical algebra, we can see that the inverse of b must be b raised to the power of m minus 2. The spell for the reverse incantation is revealed. And just like that, a really tricky division problem gets transformed into an exponentiation problem. And that's something computers are really, really good at solving. Your adventurous toolkit. Okay, let's just pause for a moment and look at everything we've accomplished. You've successfully navigated two pretty mystical realms, and you've gathered some seriously powerful tools along the way. Let's take a look at what's in our adventurous toolkit now. So you might be wondering, why does this matter? Is this just a fun story? Nope. That harmony crystal, the GCD, is absolutely crucial in cryptography for creating the secure keys that protect all of our data online. The cycle of alignment, or LCM, is used by operating systems to figure out how to schedule different tasks to run at the same time without clashing. And the magic of the clockwork realm, it's fundamental to hashing, which lets us store and find huge amounts of data super fast. And I want you to remember this as you keep going on your coding journey. The most powerful magic in programming isn't being a genius or memorizing a bunch of spells. It's having the curiosity to really understand your tools, to ask why they work, and to appreciate the beautiful patterns they reveal. Okay, so let's do a quick recap of today's quest. We started with that puzzle about the two lighthouses, and from it, we discovered the harmony crystal, or GCD. We used that crystal to predict the cycle of alignment, or LCM, making sure to avoid that nasty overflow beast. And then, we journeyed to the amazing clockwork realm and learned the reverse incantation, which lets us divide in a world of loops. You've done an absolutely fantastic job today. Seriously, the tools you've added to your toolkit are some of the most important and fundamental ideas in all of computer science. But our adventure is just getting started. In our next quest, we're going to enter an enchanted forest, a place full of winding paths that can repeat forever. They can trap you, or they can lead you to incredible treasure. So, are you ready to master the magic of loops? I'll see you then.
Hey there, fellow adventurers, and welcome back. It's me, NerdTeach, your guide for today's quest for knowledge. So, we're about to dive into this world of, well, magical mathematics, really. We're going to uncover a secret that lets programmers do these seemingly impossible calculations in just the blink of an eye. So you know the drill. Grab your thinking caps, and let's get this journey started. So you ever been playing a game, right? And there's this huge explosion on screen, or some really complex physics simulation, and you just stop and think, wait, how is my computer even handling that? I mean, it's calculating these gigantic numbers for damage, for special effects, for where things are going to land, and it's all happening instantly, without any lag. Well, let me tell you, it's not just about having a super powerful computer. Nope, it's a really clever bit of magic that we're about to learn together. Okay, so just imagine this. Your computer's quest for the day is to calculate 3 to the power of 1 billion. Yeah, 1 billion. So, the way we'd all probably think of first, is to just take the number 3 and multiply it by itself. Over and over and over again. 1 billion times. I mean, even for the fastest computers on the planet, this would take, well, pretty much forever. The program would just give up. It would totally crash. You know, in the world of programming, this really straightforward, head-on approach has a name. We call it the brute force method. And for our quest today, this method is basically a giant, unbreakable wall standing right between us and our goal. Now, programmers have a way to measure this kind of difficulty. We call it time complexity. All that means is, for this brute force method, the time it takes is directly tied to how big that exponent is. So, an exponent of 1 billion? Yep, that means 1 billion steps. We call this O of x. And let's be real, for our quest, that's just way, way too slow.
But what if we didn't have to smash through that wall brick by painful brick? What if, maybe, a wise old wizard left behind a secret, a magic scroll that holds the key, a spell that lets us just bypass the wall completely? And this, my friends, is where our real adventure truly begins.
So this scroll, it teaches us this amazing method called spell weaving. The idea is, instead of doing billions of teeny tiny multiplications, we're going to create just a few really powerful building blocks. Let's call them runes, okay? We start with our base number. That's our first basic rune. Then we weave a stronger rune by multiplying that first one by itself. And we just keep doing that. We keep squaring our last rune to forge an even more powerful one. In just a handful of steps, we've got this awesome set of mighty runes. But now what? How do we actually combine? Okay, so let's take stock. We've got these powerful runes, right? Like 3 to the power of 1, then 3 squared, 3 to the 4th, 3 to the 8th, and on and on. That's great. But how in the world do we know which of these to pick and combine to get our final answer? Well, that is the secret recipe written on the scroll.
And here it is, the big reveal. The recipe is written in the ancient language of computers themselves. Binary, yes. The secret to calculating a number to some huge power lies right there, in the binary version of that exponent. This is the key, you guys. This unlocks everything.
Okay, let's try this with a smaller, more manageable example so we can really see how it works. Our mini quest is to calculate 3 to the power of 13. Now, the brute force wall would make us do 13 separate multiplications. Ugh, but the wizard scroll, it tells us to first look at the number 13 in binary, and that is 1101. That binary number, that's our magical recipe.
Okay, this is where it gets really cool. Let's decode this recipe together. We're going to read that binary number, 1101, from right to left. So each digit corresponds to one of our runes. That first digit on the far right is a 1, right? That means, yes, we need this rune, which is 3 to the power of 1. Simple enough. Okay, next digit is a 0. That's the scroll telling us, nope, skip this rune. So we ignore 3 to the power of 2. The next two digits are both 1s, so you guessed it, we need the rune for 3 to the power of 4 and the rune for 3 to the power of 8. See? The binary number is literally a checklist telling us exactly which ingredients to use for our spell. It's awesome.
And voila, this is the magic. Instead of 13 tedious multiplications, our big scary problem has been broken down into a much, much simpler spell.
Now to be fair, we do still have to make the runes, right? But that's just a few quick steps of squaring. Then we just multiply the ones we need. So instead of 13 steps, we're down to what? Just a handful? Now just stop and imagine the savings when the exponent is 1 billion. It's a total game changer.
Okay, let's just pause for a second, take a deep breath. If your head is spinning a little bit, or if this feels kind of tricky, that is totally 100% normal. It's a completely new way of thinking about a problem. That feeling of confusion, that's not a bad thing. That's just a sign that your brain is firing up, building a brand new, powerful connection. Trust me, every single programmer has felt this exact way at some point. You are absolutely on the right path.
So now that we've got the story, the magic behind the scroll, are you ready to see how a real programmer would write this spell? Let's take our storybook logic and translate it into some actual code.
All right, let's break down this C++ spell. So that while loop, that's basically us saying, hey, as long as our exponent is still bigger than 0, we need to keep reading the recipe. Makes sense, right? Now, inside that if statement, that's how we check the very last binary digit. If that last bit is a 1, it means our recipe is yelling, use this rune, you need this one. So we multiply our current base into our final result. Simple. Now, after that check, whether we use the rune or not, we have to get the next one ready. That line, base times equals base, that's us weaving a stronger rune by squaring it, just like we talked about. And finally, x equals x by 2. This might look a little weird, but it's our clever way of moving to the next digit in the binary recipe. It's like sliding our finger one spot to the left on the magic scroll to read the next instruction.
Okay, but wait, there's one more crucial piece of magic we need to talk about. When you're dealing with these gigantic numbers, like our original problem of 3 to the power of a billion, the final answer can get so ridiculously huge that it literally overflows the computer's memory. You can think of it like our magic potion is bubbling over its cauldron, just spilling everywhere and breaking the whole spell. So to stop that from happening, programmers use a special containment charm. It's called the modulo operator. Just think of it as a magical force field that keeps our numbers from spilling over. It makes sure everything stays within a manageable size, so our spell works perfectly every time, no matter how powerful it gets.
So, the big question, just how much faster is our new spell? Well, this chart pretty much says it all, doesn't it? That super tall bar, that's the brute force method. Its time just shoots up and up with the exponent. But that tiny little bar next to it, that's our spell weaving method. Its time complexity is something programmers call O of log expo. Now don't worry about the fancy name, just look at that difference. All it really means is that even if the exponent gets a million or a billion times bigger, the number of steps we need to do barely goes up. It grows so slowly. It's just insanely efficient.
And I really want to make this clear. This isn't just a fun little storybook trick. This algorithm, its real name is binary exponentiation, or sometimes exponentiation by squaring, is an absolutely fundamental tool. This is real-world magic that professional programmers use every single day in things like cryptography, game development, and competitive coding to solve massive problems in a flash.
So by understanding this, you've basically just leveled up. You've gained a new set of magical powers. Seriously. Now you can spot and solve these tricky interview questions that totally stump other people. You get a key piece of how things like cryptography and video games work under the hood. But maybe the most important power of all is that you're learning to think like a programmer, which isn't about working harder. It's about finding these clever, elegant shortcuts to solve huge problems.
And that really brings us to the most crucial point. Remember, you don't need to be some kind of genius to code. It's not about knowing everything. It's really about finding clarity, about finding a simple path through a complex problem. And sometimes a good story is the best map you can have. You've totally got this.
All right, let's do a quick recap of our quest today. So first, we came up against that unbreakable wall of a massive calculation. Then, we discovered the wizard scroll and its secret recipe hidden in binary. We learned how to weave powerful runes just by squaring the base. We even wrote the spell in both C++ and Java. And finally, we brought that new power back to the real world. I'd call that a very successful quest.
Hey, thank you so much for joining me on this adventure today. I really hope you're feeling curious and ready to learn even more, because on our next quest, we're going to venture deep into the prime forest to uncover this ancient, really beautiful method for finding every single magic number out there, the sieve of Eratosthenes. It's going to be great. Until then, hey there, fellow adventurer, and welcome. I'm NerdTeach, and I'm so glad you're here. We're about to set off on a classic quest, one that pretty much every single programmer takes on, but this one's got a hidden trap. It's a puzzle so sneaky it can bring even the most powerful computers to a grinding halt.
But first, let me ask you something. What if I told you that a tiny little piece of code, I'm talking just a few lines, could take longer than the age of the entire universe to run? I know, it sounds completely made up, right?
Well, here's the thing. It's totally possible. In fact, it's a trap that so many of us fall into on one of the most famous quests in all of programming. But hey, don't you worry for a second. Seriously, every great programmer once felt totally lost right here. Confusion just means you're learning. We're going to tackle this together and find all the secret paths to victory.
All right, let's get into it. Our mission today is to figure out the architect's blueprint for the legendary Golden Tower, and this whole blueprint is built on a magical set of numbers called the Fibonacci sequence. To even think about climbing this tower, we've got to understand how it's built, step by step.
So, what is the big secret to building this tower? You know, it's actually a super simple rule. You start with two basic steps. The first one has a height of 0, and the second one has a height of 1. From there, every single new step you build is just as tall as the last two steps added together. We can even write it down like a little magic formula. The height of any step n is just the height of step n minus 1 plus the height of step n minus 2. That's it. Simple as that. Let's just build a few steps to see how it works. Okay, so we start with our foundation, steps 0 and 1. To get the next step, step 3, we just add them up. 0 plus 1 is 1. Easy. For the fourth step, we add the 2 before it. 1 plus 1 is 2. The fifth step, well, that's just 1 plus 2, which is 3. And we just keep going. 5, 8, 13, and all of a sudden, whoa, our tower's shooting up into the sky, all from that one little rule. Okay, so how do we actually write a program to figure out the height of, let's say, the 50th step? Well, the first path that most of us try is the most obvious one. It follows that rule we just learned perfectly. But as you're about to see, it is an exhausting climb. Okay, picture this. To find the height of step 5, my code has to ask for the height of step 4 and step 3. Makes sense. But wait, to find step 4, it has to ask for step 3 and step 2. And to find step 3, it asks for step 2 and step 1. Do you see what's happening? My program is asking for the height of step 3 twice already. We're doing the same work over and over and over again.
Now, this technique, where a function actually calls itself to solve a problem, is a really powerful programming spell. It's called recursion. It's kind of beautiful, honestly, like looking into a mirror that's reflecting another mirror, that's reflecting another mirror. It just breaks a big problem down into smaller and smaller versions of itself until it hits a super simple answer that it already knows.
So here's what that spell looks like in C++. We make a function, let's call it fib. The first thing we do is set up our bottom of the mirror, our base cases. If the number n is 0 or 1, we just return n. That stops the whole thing. Otherwise, and here's the magic, we return the result of fib n-1 plus fib n-2. See, it's a perfect copy of our rule. But it's also where the hidden trap is.
And if we look at it in Java, well, it's pretty much the exact same idea. We check for those base cases to stop ourselves, and if we're not there yet, we make those two recursive calls. It looks so clean and elegant, but for our poor tower, it comes with a terrible cost.
And that cost, it's time. A lot of time. This path is just plain exhausting. Because we're recalculating the same values a ridiculous number of times, the work just explodes. This is what's called exponential complexity, or O of 2 to the n. And what that means in the real world is that your program starts to crawl and then it just stops. It freezes if you ask for anything bigger than, say, step 40 or 45. The tower just becomes completely unclimbable.
But what if we could be smarter about this? What if we could learn from our own work instead of forgetting it every single time? Well, that leads us to a much, much better path. I like to call it the path of the memory stones. The idea is actually super simple. The very first time I figure out the height of a step, let's say it's step 3, I write the answer down on a magic memory stone and leave it right there. Now, the next time any part of my program needs to know the height of step 3, it doesn't have to do all that math again. It just looks at the stone. All that repeated work, gone.
This amazing technique of solving a big problem by solving all the little pieces first and saving the answers has a really cool name, dynamic programming. So instead of starting at the top of the tower and working our way down into that recursive mess, we're going to start at the bottom and just build our way up, one step at a time, using a simple loop. We only ever need to remember the last 2 steps to figure out the next one.
Let's look at the C++ spell for this path. It's so much simpler. We just make 2 variables, a and b, and start them at 0 and 1, our first 2 steps. Then we just loop from step 2 all the way up to our target, n. Inside the loop, we calculate the next step, c, by adding a and b. Then we just update our memory stones. A becomes what b was, and b becomes our new number c. We're always ready for the next calculation. It's clean, it's simple, and it is lightning fast.
And again, the Java spell looks almost identical, doesn't it? We set up our 2 starting variables, we loop up to our target number, and we just update our values as we go. This is like a straight, confident march right up the tower. No detours, no wasted energy.
So let's put them side by side. The endless climb, our first recursive path, looks beautiful, but it's painfully slow for any real tower, because it keeps redoing the same work. But the path of the memory stones, our iterative path, is just plain smart. It remembers what it did, builds up one piece at a time, and is just way, way better for climbing a tall tower.
But what happens when the quest gets truly epic? I'm not talking about the 100th step or even the 1000th. What if the tower reaches step number 1 quintillion? That's a 1 with 18 zeros. Our loop would literally take centuries. For a quest like that, we need something that feels like actual magic, the teleportation scroll.
Okay, this magic has a big, scary sounding name, matrix exponentiation. Now don't let that name freak you out. I was totally intimidated when I first heard it too. Just think of it like this. Instead of climbing 1 step at a time, what if you could take these massive leaps, basically doubling your height on the tower with every single jump? That is what this technique lets us do.
So how does this crazy magic even work? Well, it turns out you can squish our add the last 2 steps rule into a tiny 2x2 grid of numbers called a matrix. And here's the wild part. If you multiply that matrix by itself, it's like taking 2 steps up the tower at once. So if you raise that matrix to the power of n, you jump straight to the nth step. Using a clever spell called fast exponentiation, we can do this in just a handful of jumps, letting us teleport to an impossibly high step. Whew, okay, so we have seen 3 totally different ways to climb the Golden Tower. And the lesson here isn't about which one is the best. It's about realizing that you, the adventurer, have a toolkit, and a smart programmer knows exactly which tool to pull out for the quest at hand.
And here it is, our adventurer's cheat sheet. The endless climb, that O to the N path, is basically a non-starter for any tower taller than 40 or so steps. The memory stones, our O of N path, is fantastic. It'll get you up towers with hundreds of millions of steps, no problem. But for those truly legendary quests, the ones that go into the quintillions, only the O of log N teleportation scroll will get you there.
So let's wrap up our journey. We saw how a really simple, beautiful idea can actually hide a terrible performance trap. We learned that by being just a little bit clever and remembering our past work, we can build a solution that's fast and reliable for almost any quest you'll face. And we even got a peek at some high-level magic for challenges that seem completely impossible. Remember this, the goal isn't just to find any answer, it's to understand the different paths and choose the right one for your quest. That right there is the heart of thinking like a program. Thank you so much for joining me on this adventure up the Golden Tower. I really hope you're feeling a bit more curious and maybe a little less scared of these big ideas. In our next quest, we're going to venture into a brand new forest, a tricky place where loops can either be your greatest shortcut or a trap that holds you there forever.